All right, this is part 2 of the battery analysis. And in this part, rather than going through the, the load shapes and how big a battery do we need to fill to combine with solar power to meet different sorts of load shapes. By the way, of course, you could have done this for wind as well. And remember, we did this only for one single hour. Now, what we're going to do is work through the cost. What's the capital expenditure or the capital cost? What are some characteristics of the battery in terms of life, in terms of degradation, and even taxes and cost of capital to come up with what's the carrying charge. This is all going to be changed as we make the video. And ultimately, we'll do this for solar and battery and then compare it to some kind of all thermal, whether it's natural gas or whether it's a coal, not coal. Oof, we definitely have to add emissions then. But what if it's diesel, for example, on an island or something like that? And then we can put solar plus battery together, and eventually we can put solar plus thermal together. And hopefully, sorry about that loud noise. Okay, and hopefully we'll be able to illustrate what happens. We're going to have to use extra solar. You'll remember the maximum load we had was 41, but we had to put 171 of solar. If we only use thermal and solar, we'll put a much smaller solar project in and use the balance of the, because we can't store the solar with the thermal. We can't suck out solar power and stick it into a natural gas plant or a diesel plant or something like that. So we're going to go through that. And then instead of me obsessing about how do you model the degradation, how do you model the tax shield, how do you model the timing of the construction, how do you model the inflation and get this into appropriate real costs, not the crap, the complete, utter, and total complete crap that Lazard gives you, where they don't tell you whether it's real or nominal. And any economic analysis, you'd be better using real cost adjusted for inflation. Okay. Ooh. And the other thing we can talk about a little, no, I'm not going to talk about it, but I'm going to tell you is if you're using a pure project finance approach and never assume refinancing, that's going to be a problem. And we're going to adjust the cost here for the duration of the battery. And then we're going to recognize, just like in any model, that we have absolutely no clue as to what really is going on, especially with batteries. And we're going to try to put different inputs in. And when we put different inputs in, we'll make a scenario analysis. And I might have to, that might be a pretty long thing to do. And ultimately, I want to get to the answer now. I'm going to make a preliminary video to this where I've given you the answer. So let's proceed. Okay, the very first thing let's do is recognize, well, okay, when we did this in part 1, we said, okay, we get this for our solar. This is the amount of solar we need if we're going to have solar plus battery. So maybe we put solar for solar with storage, and eventually we'll put solar without storage, and that's going to be a different number, and people will be happy who really like solar to say, we need a whole bunch more with storage. Without storage, the amount of solar we need, again, we're doing a lot of simplification, and we're leaving the elephant in the room about the fact that different projects have different days have different amounts of solar power. And remember, we were able to kind of put this little thing in where we said our solar power day. So why don't I insert a couple of, what am I doing? Inserting in the wrong place, maybe. We'll put our date for our solar power. And remember, we'll be able to click on these things and copy them. And so we can try different years and different months and get different amounts. And maybe we should even get a little fancy and take our solar power pattern. You remember this, and now I took a pattern I don't really like. I press alternate F1. People seem to not know that little obvious kind of trick. And I cut that and put that somewhere right here. Maybe I can make a really little one. Now, when you make oh, that's almost too big. Maybe I'll put it here. And, shoot. Okay, it's so small, but if you go to the home page and maybe change this to 2 or something like that, then at least we can kind of see what's going on with this one. Sorry about wasting a little bit of time on this. Okay, so we'll go back to 2009 and put our kind of, is that a good solar pet year? 2008, that was even better. The financial crisis year. Maybe that financial crisis affected the solar power. And then we better do our little thing where we shade this, and let's put 6 at the top. And I said 6 at the top, didn't I? 5. Okay. And let's make our... So we can see that we've taken this one from another sheet. We've taken this one and we've done this analysis, and this turns out, was a kind of crap year to do. So let's put it back to 2010, and we, for some reason, that almost looks funny, 2010, that we had so much, and we can, depending on what solar, and let's put the solar capacity factor. Let's put the capacity factor. Now, when we get to the battery, I think I'm just going to leave that out. But we're going to be able to say, okay, what happens if for this day we have a different solar capacity factor? Now, clearly, if we have a lower capacity factor, we're going to have a dramatically different battery storage. So I'm going to kind of cheat and use a pretty high capacity factor. If it's the all thermal unit, well, our capacity factor is really just the same as our load factor. And in this case, if it's all flat, we'd have to run it basically at every hour of the year. But if it's shaped, then we'll only use our thermal plant 31%. Remember, this capacity factor for the solar was affected by the performance ratio and the fact that the STC is the basis for our measurement. And then we get the amount of battery. And what we did last time is I'm pressing Control in the square bracket, and then I'm pressing F5 to get back. And it tells us how much our capacity and our storage has to be for different amounts for different shapes. Okay, and just by doing that, I know it's a relatively, it's got the same, it's got the elephant in the room problem, because we don't have, we're not recognizing that we have different solar every day, and we've got uncertainty, and we've got to store for If it's rainy days, we've got to store for a lot more than a rainy day. Okay. And then we have our total production. And why, if it's all thermal, actually we could just multiply this by the capacity factor, and then we could multiply it by 24, okay? Perhaps we should get used to that. And when you add these two together, as the solar plus the battery, we can see, well, how much production, and we got exactly the same amount, okay? That's our starting point, and I'm trying to do this on a fair way, and we could put megawatt hours per day. I don't know if you should really put a divide sign here or not. I hesitated. Or you could put MWD. Maybe that's a better way to do it, okay? Eventually, when we put the solar power without the storage, we can actually, why don't we go and do that now? We have our solar capacity factor, and then we can put in our multiply our solar capacity factor by 24 and get that. I hope I'm not doing this too much, and then we'll put our thermal for thermal. I put slash storage. Okay, and that means, well, we've got to get the total amount minus the amount we produce for solar. Okay, so we get started here. And now let's work through the cost. And for the cost, now I put this as a sensitivity case, and I suppose let's do that. I don't know. I was debating how to do that. And then I put, well, we can get our shape data. Let's leave that out for a minute. We can get that one, and let's leave our battery dispatch out for a minute. We're going to discuss the battery cost, and let's start with our solar cost. And did I put the solar way over here? I put the solar way over here, so let's press Control X and move it over to this one. Okay. And we put our solar cost in. All right, that's the first thing. So I'm going to take this, and then I'm going to put, maybe I could put a high solar case, a high solar cost. And this is just amazing that the countries are so different. I can't put 1,000, but you know, all these people give me 900 for the cost in the US and all that stuff. Okay, and then eventually we'll do this. We'll put a code number, and this is scenario analysis 101, and we can go down here and put index, and we can select all of these things and put our code number in, and that's really the number we should take, and then we can start working on all of our characteristics. And so when we put the cost of the alternative, this should come from the sensitivity page. And maybe I'm going to make our sensitivity page, what color should I make it? This is an enormous decision, but I'm going to make it purple. And then I'm going to make our load, what color should I make that? Let's make that, how about a really dark orange? Okay, and then now when we press Control-Alt-C, if you put the tab color of the sheet, then you can see, which sheet did it really come from? And the purple ones didn't work very well because you can't really see that they're purple. Oh, this is such a big deal. Oh my gosh, and I'm wasting so much crap time on this. Sorry about that. Let's try that one. Who knows what that will look like, and then I'm going to stop, of course. I said, of course, I probably won't. That's good. That's still no good, but we can see where they come from. Okay, and then, then when we get to the battery cost, well, let's put number one, a battery sensitivity. And no. I'm going to do it like this. Sorry about changing my mind in the middle. When we put our sensitivity case for the battery cost, I started last time to really talk about this stuff. And what the battery cost is now and what it is going to be in the future are big deals. And I'm going to keep working through some of the battery characteristics. And instead of just throwing cost in, we'll talk about this. Now, if that battery cost was 100 per kWh, that would be great. It doesn't say here what the duration is. This is for a 1 hour duration. And for a 1 hour duration, this says that in 2026, we're going to get 277 instead of 100. And they add in all these transformers. Well, that's fine. But then they add in all the EPC costs, the developer margin, the developer overhead. Oh, God. Okay, I've already talked about that. And then I showed you this thing, and I made a little slope and intercept. And we have more examples of how the cost is different with different durations. And in this case, we've also got a very interesting thing that says the bigger the battery, the lower the cost. So we've got some interesting economies of scale that are apparently different for different batteries. Why there would be so many economies of scale is kind of a curious thing. And this is another thing that suggests there are economies of scale. So if we would do our real analysis, we would reflect both the economies of scale and the fixed and variable. Now, instead of doing that, what we can do is put in a slope factor. And what I did here very quickly is just to say, here's the y, which is the cost, x is the duration. Let's do a slope and intercept and get a straight line. And if you do that, it suggests the equation for, and that comes from that graph I showed you, the equation for the cost per kW is a fixed number minus, as you get bigger and bigger hours of duration, it goes down. And so if we have 2 hours, the cost is 458. And then we can put in our slope and our intercept and maybe try to analyze some different relationships. And we'll get that number. And then we can put in up here the duration. Okay, and now I'm kind of going back and forth, which might not be a really great idea, but I'm going to do it anyway. We got the duration from our other analysis, and we just take this plus, I'm sorry, the final cost is we've got to copy this over, and the final cost is the fixed plus the variable times the slope times the duration, and then let's use that one for our cost. So let's get the cost. Now it's all connected. And now if we make it a flatter thing, our battery, a flatter load, because we need more hours, the cost per kilowatt hour goes down. And for the thermal, let's put some thermal in here. And let's put maybe over here, let's put a thermal cost. Now poor old thermal, nobody can sell this stuff. So let's put the cost per kW, and this is 800. Okay, and we've got the cost going on. By the way, up and on. Okay, now once we have that, we'll connect that. So now we've got the kind of costs in here, and then I'm gonna connect these with a LCOE calculator. Okay. And if this is too boring, I'm really, really sorry. But instead of, so we multiply for the solar, we multiply the cost times the kilowatts. For, again, this assumes every single hour is the same. And maybe up here we should have really put total production per year. And I think we can assume either we can assume either 365 days or 365.25 years. Let's show how smart we are, because we understand there's a leap year. So let's multiply this by 365.25. Okay, and okay, I don't think I need decimals on this. All right, and that's how we're setting up. I hope this is okay. And if somebody says, "Oh no, you're going too much details," I'm going to try to avoid the details. And I hate doing this because I'm going to try to avoid the details, and we're going to throw the capital expenditures right in here. Now for the if we put the thermal with the storage, we need the same, we still need the same amount of capacity. We still need to pay 800, and this time it's a little bit trickier. So this is our cost. We need to put in 100 for our, or we need to put the total amount. I'm sorry. We need to put the total maximum load. I got that wrong, and that's why I make these kind of mistakes here. And then we can get the upfront cost. Now, if we have a flat load, you notice the battery costs a lot more than if we have these alternative loads. And so I'm trying to do it correctly for once and really get the answer. And really get the answer for just, because usually I tail off by the end and don't give you the answers. And then we'll take all of these costs. Now I'm going kind of back and forth, and you can say, this, you're doing such an idiotic thing. But we're going to put in those capital costs into our calculator. So instead of going through all of this, doing this, going through all the capital costs, let's just put the capital cost of the solar and then the capital cost of the battery. And we're going to put the capital cost, if we go all thermal, here. So we've got more capital intensity, and that's a big deal to really understand. And then finally, thermal, for solar. And we almost don't need this one because it's going to be exactly this. Well, it's going to be different, but when we divide it out, it'll be the same. Okay, so that's what we start with, and then we've got to put our operating life, economic life. I should even call that economic life. And then we'll put our tax life, we'll put our tax depreciation, we'll assume debt to capital, and we assume we refinance all the way to the end instead of a project finance, which means we can use this weighted average of all the debt that stays at the debt rate and the cost of debt, and we'll put an after-tax cost of debt in and get all our IRRs. But the very first thing we need to do is go and get the tax life. And I think I better pause the video because I better pause. I've got other Just a minute. Yeah, I'm sorry, guys. I had an interruption. I thought somebody charged something on my stupid account, and then you're on the phone for 5 hours on this little crap thing that I don't know. Is the world really that much better today? Okay, I was interrupted for a long time, and now I'm back. And you'll be happy about that. And I was told my microphone sucks, and sorry about the quality and everything else. And now, so the next issue is what are the real operation and maintenance expenses on a battery? And that's, I think, a little bit of a controversial kind of a subject. There's a whole lot less information you can find on the O&M expenses. Lazard, oh God, these people who, I don't know if you should believe much of what they do anyway, after they came up with this hydrogen report. But they put somewhere around 1.3%, and I did some other analysis, and we'll put that's 1.3% of the capital expenditure. So I'm just going to put that in, and perhaps you you might want to dispute something like that. But let's put that over here and put some operating expense percent, or yes, I'll put that for the batteries. Okay, for the other ones, we'll do it differently. And it seems that, oh, whoops, and I'm going to put that again in the sensitivity case. And here I put 1.5%. I'll put 1.3% since I told you that. And we'll do at least some sensitivity analysis on that. But we can see 1.3% is not a big percentage of the capital. Now, the next issue is what is the lifetime of a battery, and this is a more difficult one. Okay, I can't emphasize the importance of this. If you buy a electric car, a Tesla, and you have to replace that battery, you might in a short period of time, you may as well, I think, probably throw out the car. You can you can kind of figure out how many kilowatt hours the car uses, multiply this by our 200 or 400, whatever you think the kilowatt hour charge. You multiply that out together, and you get a very significant portion of the car is the battery. And if you have to throw away that battery, if you have to replace that battery and pay for all the installation charges and everything else, it can be really bad. So if the battery has a long life, it's a really important issue in the whole world. Some people say, they can get a warranty. Now, one study says the batteries for a lithium battery last 20 years. I don't know. I should really put the sources of some of this stuff, but if you order like you're going to pay, no. You send me an email and I'll give you all the studies that I collected this from. They're in a folder. But then if you read another study, NREL, who must love batteries, some people say 5 to 15 years. And I always ask people, well, it's the same lithium battery you have your phone. You think your phone really is? You're probably going to. I have to throw my phone away right now because the camera went out. I smashed it or something. But a lot of times you might have to replace your phone. Well, I dropped my phone in the toilet, so that's why I had to replace another phone. But sometimes you have to replace it because the battery is going bad. And the battery can go bad because it's taking a whole long time to charge, or it kind of just doesn't work hardly at all anymore. So some people say, and you can define the life so many different ways. It's 5 to 15 years, not 20 years. And NREL, it's 7 to 10 years. And that's if it's cycled within a 47% depth of discharge operating range. And we have to include the depth of discharge. And now, we if we're a little more precise, I understand that if you have a battery and you just don't leave it somewhere, like I left a battery in the garage, that will still be okay. It depends on how many cycles you charge, so how many times you charge and discharge. And this estimate said it's 4,000 cycles, so if we do it every single day, like we're kind of assuming, that gives you a lifetime of 10 years. We obviously have a big variation in the a life estimate. Okay, and if it's 6,000 cycles, okay, 365. I don't know if you take 6,000 divided by 365, you get 16. And then there's some other comments. This is from a Department of Energy report. And we have the 16 years again, and 5 to 20. And it's clearly an uncertain kind of a thing. And this is a MIT study, and we have the blah, 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 lithium battery 5 to 15 years. It's clearly a big deal, and it's extremely a big deal. And then you can look at our famous Lazard thing, okay? And what we're going to do now is I'm going to go to our sensitivity page, and instead of doing this, I'm going to copy this and put longer battery life, and I have to spell life, okay, and then we'll copy it and put a shorter battery life. And we're going to do this with all of the different kind of variables. And so let's put 20, and let's do a sensitivity and see what happens when we change this. So of course, all I have to do is press number 2, and that's why I said and stupid thing, I didn't. What index? What? Oh, in that. Why? Just a minute. D7. Okay, that never's happened. Well, duh, I put 12. Okay, that's what happened. So if I put 2, I get 20, and I put 1, I got a different number. So we can start. This is, we need to kind of recognize that we really don't know some of this stuff. And this variable will come from over here. Okay, and we're going to put that in. Now, the next issue in what we'll do next is when we plug this, I didn't finish the O&M expense. I'm sorry. Fixed O&M expense. Now, I'm going to do this really quickly for the solar and the thermal. I'll put USD per kilowatt dash year. Okay, that means it's a fixed cost, and for the solar, I'm going to put about 10. And what we have to do is something that Lazard doesn't do. It's not just O&M. It's if you're using levelized costs, you can't pretend accounting costs don't exist, insurance costs don't exist, land costs don't exist. It's got to include all that stuff. In batteries, it does too. So we've got to be really careful. We're not going to put anything for batteries because we included this, and maybe I'll put about 6 for thermal. That's an estimate. You can go to a whole bunch of different places and get there, and I'm not taking that from the sensitivity page. And then we can put, now that let's put a heat rate for thermal. Now what I do is I use MMBTU per per megawatt hour. And I've discussed this so many times, I'm not going to do it. And if it's a diesel unit, maybe that's something like 10. If it's a combined cycle, maybe it's about 6.5. Let's start with a gas combined cycle plant, and we'll adjust it later, and then we'll put in the a fuel cost per MMBTU. Okay, and that you can get from a lot of places, but one of the places you can get it is if you go to my website or to the disk, and you go down to the one that says databases and data retrieval, and if you go and get the one called commodity price, and you get the one called commodity price analysis, I did this originally in a class, and the fascinating thing I want to show you is the spike in the price of gas in Europe relative. Look, Europe went down to the same price, natural gas price, as US. Let's focus on it a little more. And you can just automatically update this data and do your little correlations and get your flexible graphs. And I hope somebody one day will look at this and use this. You can, of course, do all the analysis yourself. You're just going to the internet and grabbing it. If we compare the gas price in Japan to the gas price in the U.S., there has not been that. This is only through, where does it say? Last value. It says the last value, which is here. It's August, okay? And I think it's gone even higher. We've got an immense spike happening. Okay, that's the price of gas. So if we put in a price of gas of 18 versus in US, in US 4 or something, we're going to get a very big difference in our analysis. And I'm pressing Control Tab, and I'm going to close that file. And I purposely did that because I want you to see where this stuff is, and I want one person in the whole world to maybe use it one day. And so for the thermal, let's put 10. Let's put a really, really high gas price, and that might be something like a diesel, a mixing up kind of diesels. And then I press Control D, and we can put the fuel cost per MWH and USD per MWH, and we just multiply the gas price times this, because MMBTU per megawatt hour multiplied by USD per MMBTU gives you the number. And then we can put in our total O&M. Let's go up here and put our fixed O&M. Okay, how about I'll put our total fixed O&M expense, and we have to be a little bit careful because we have this thing. I said this was a megawatt, and we said, okay, well, this is the amount of solar we need. We're paying $10 US dollars per kilowatt, so we better multiply that by 1,000. So we have all the units consistent. Oh God, I hate doing this. And then we can put that in for our thermal, and for our battery, let's just take 1.3% of the. Oh, I can't do this. I would scream at people for doing this. So we have more O&M on the solar than on the battery. If we put a flat one, we have almost the same. If we put off peak, we can see what happens. And then when we put our fuel cost in, we need to know how many megawatt. This is megawatt hours per year. Okay, and we have the cost per megawatt hour, so we can put the total fuel cost. And if anybody, this really is the theme as usual, is that if anybody says, oh, it's too complicated to compute LCOEs, oh no, you can't do it. What a lot of junk. You can get the numbers, and of course this, I say of course, and I shouldn't say of course like this, but there's the key difference, because I didn't understand it for so long, but there's a enormous difference between the capital intensity of any kind of thermal unit, but especially diesel or gas, because we have a very big O&M cost and a much smaller capital cost. So now you can put total O&M cost, and we'll put that in USD. And for our solar and our battery, we don't have any fuel. That's why it's so good for the environment and everything else. And then we can go, we've kind of got the big items here. Here's our capex, and here's our O&M cost, and we can plop that into our detailed LCOE calculator, and we've got a kind of fixed number we can just put in. So once you have the calculator set up, isn't that kind of cool that you can just get the total cost? And I'll put the total cost for our final one in here. Okay, and then now the next thing we can do is we can go, and again, I'm not redoing all the analysis and going through all the PMT calculations and everything else to get these things right, but we could put in our lifetimes. And I made a long lifetime of solar, and of course, you might disagree with that. And then we'll put in our lifetime of our battery, and our lifetime of what happens if we use all the thermal load. And I'm just trying to get a comprehensive kind of analysis finally done. I really want to do this to see what's the answer, how much, if we change the fuel cost and we change some of these parameters, what's going to happen to the whole thing. I'm going to leave a short tax life, and we'll put in our tax rate. And did I put this in already? So you put your own tax rate in. I'll cheat on this one and just give everybody the same tax rate. And we can put an accelerated depreciation factor in. Suppose I'll even do that. That's where you might have this thing called a double declining balance, and issues like that. And I'm purposely not going through it in detail, because I've gone through the detail in other videos, and it's kind of boring anyway. And then we can put debt to capital in, and ultimately, when we put all of those factors in, we'll get how much capital has to be recovered every single year. And it's going to depend if we can get a low debt cost and get a high amount of debt, and we can get from there a low IRR, that's going to be a big deal. And we have to put the inflation rate in too, so we can compute these things on a real basis. And we also need to get the degradation in. Now, for degradation, let's put kind of a classic number in for solar. I'm not saying that's always right, because I know there are there can be disputes about this, and I know banks, for example, will do this. But when we get to the battery, that's when it becomes a little bit more, should I say, intense, because that one we don't know exactly how it's going to be. And this is an issue for cars too. If you read the reviews, somebody from said, I've experienced a whole bunch of degradation in my first year, and somebody else said, no, that's right at the beginning. After that, it degrades much less. How much degradation will you get? And they say, well, here it can be 2 to 4% per year. That's a lot. That's a lot more than solar. And and maybe and then the we also have to adjust the capacity for depth of discharge. Here's what some people say it is, and notice that what we can do, and I should have put a little comment here. If the degradation in 10 years goes down to 78%, you can take 0.78 raised to the 1/10 power minus 1 and figure out what the annual degradation is. And you can do that over 15 years. And it's not constant, really. There seems to be a bigger degradation as you get older and older. And maybe that's really why people are saying the life is kind of different. Here, there's some different degradations I have, and I suppose I'm gonna put I'm gonna use this one. I'm gonna put I'll put 3%. And then we could also make a scenario. So let's put 3% as our base case. And did I haven't put the degradation here. Okay. And we'll put 3%. And I hope you say, oh, yes, we're finally doing something really comprehensive. And we just copy it over here. And this shows you just setting up a sensitivity case almost right when you do this. And then we can put a lower degradation to make it a little more positive, and we can put higher degradation to make it a little less positive. And then, of course, what did I do? I meant to when we this duration should always be taken from the same thing. That was a little bit bad the way I did it, maybe, but who cares? Don't be an Excel bureaucrat, please. Please don't be. Just if you have to do things a little bit differently, that doesn't matter as long as you're clear about what you're doing. So we've got the difference in cost, and we could put a cost sensitivity as well. And let's put that to be 4%. So if we now put a scenario, 1, 2, 3, 4, 5, here, I'm just going to put 1, 2, 3, 4, 5. This is higher degradation. And you just take and you select the whole thing, but we're going to add some more scenarios. So let's leave the extra potential, and let's do something a tiny bit dangerous, because this can slow you down if you start to have too much conditional formatting. But it's so nice if you do it well, and you put the scenario number in and you make that equal to, and then you press F4 a couple of times, and you keep you want to make the 7 flexible but the E the same, and then you do a big challenge, which is, what color should I make it? Okay. And then you press OK, and we can see, okay, if we use our case number 3, it's a shorter battery life, and 4, we can see exactly what scenario we're on. And when we put our analysis together, let's use our sensitivity case, admitting that we're not so arrogant that we think, I know exactly the number and I'm going to argue it till I go crazy. No, we're going to put this different. We're going to have a drop-down box that goes through the different scenarios, and then the degradation influences the battery. Okay, we put an equal sign, and we'll get that from our first page, and we get that one. Okay, now the next, and then I'm going to pause this for just a second. I'm going to throw in all the finance. Okay, now I put in the cost of capital, and here's we're starting to get to the end, thankfully. 2 hours of this stuff, and I put in different cost of capital. Now the cost of capital is really, really important for the solar and the battery, because they're solar even more important because they're more capital intensive, longer life, all capital, no very little operating expense relative to the capital. For the thermal, we have a big fuel cost. Okay, and mechanically, here's what I did. You can see when it's red, it comes from the red sheet. I went crazy. And in this red sheet, there were some numbers where we did all the detailed calculations for the cost of capital and the inflation and everything else. I've gone through that elsewhere, so I'm not going to repeat it. And what you do is eventually you get the capital recovery in real terms after the inflation. And it's absolutely essential, as I've discussed elsewhere, to get the inflation out. And this is going to go back to the other sheet. We're going to get the operating costs in, adjust the operating costs for degradation, and get an adjusted real operating cost, and that's going to go back to the other sheet. So once we have, this is the, if there's any chance you're still watching this video where I go back and forth and just blabber on, if there's any chance you're still watching this business of being able to have a little calculator for our levelized cost of anything. We put in the capital cost, we put in some of the financial operating assumptions, we get back the nominal capital recovery and then the real capital recovery. We put in the operating costs, and then we get back the real adjusted costs. And once you have that, you're just about finished. And here's why you're just about finished. We're putting in the capital expenditures, and now we introduce those and discuss those a lot for the different kind of technologies. We input the operating expenses and get back the operating expenses adjusted for degradation, basically, if they're real, if we're doing a real analysis. We put in the cost of capital, and we get back, by using the total capital expenditure and our cost of capital assumptions, we get back the total amount of capital recovery. And now we can do it with different lives. We could even put different tax rates in and different depreciation factors in, but we get the result out. And this is what I'm doing. And then we can take the total amount of our production per year. Since these costs are per year, we better get our production per year, and then we get our various different outputs. And when we start with our first case, we're I'm a tiny little bit. Oh, I saw something. Oh shit. Okay. Shit. So while I was losing it there just for a minute, I'm not going to go back and change the video. I had not connected the lifetime correctly for our alternative solar projects. And I suppose right now we have a little bit of a high cost of capital for our solar project. If we have put a lower cost of capital, oh, it didn't make that much of a difference. But we have about a 2 USD cents, $23 per megawatt hour for our different projects. And again, I have gone through all of the technical details with the connecting things. And maybe this is half what this video is really about, is how to then take that and make some scenario analysis and make some good presentations and not get trapped by the bureaucracy of people who say, oh, you can't put the scenarios together like this, you can't do the spinner boxes like this. And now we are just about finished because we have the total operating cost and the capital cost. There is one more thing though, and that's to incorporate in our analysis two additional factors about batteries, and one is the round trip efficiency. You might think, oh, that's not a big deal. This is this idea that when we have to put more power into the battery than we'll get out of the battery. And before, when I presented this whole analysis of the balance of the battery, the opening balance and the closing balance, there was no adjustment for this round trip efficiency. Somebody else said, oh, good, they use Lazard. Oh, shoot. But a lithium is 0.86 to 0.9. Other people, this is presumably lithium. This is 0.89, 0.9. Somebody else did some analysis and had a lot more losses. And again, just like all of these other variables, there seems to be uncertainty associated with it. Now, when we model the loads, and I suppose my initial objective of this whole analysis was to make it really, really simple, and I ended up, and that's maybe because it is a little more complicated. We have to, if we have some round trip efficiency losses. Now I made that very extreme, so let's make that 90%. Oh, excuse me. I did round trip efficiency 90%. Remember, we have our scenarios, okay? And just to let you know, now we can kind of look at the result. Here is the key result, kind of the solar plus the battery is 80. If we use a different solar day, we'll get a very different result. Let's find a moderate one. Here's 70. Okay. We're not beating, this is really sad, even though our solar is really, really low cost, we're not beating the all thermal. And I'm sad about that. If we didn't have round trip efficiency, I'm looking at this number, even that 10% is that's quite a big number. And our round trip efficiency, again, comes from some sensitivity analysis. So I'm trying to illustrate to you with this model and this analysis that these things can make a pretty big difference. Well, I guess I am doing that. And if we put, I'm really trying to tell you something that I have a class tonight, and they're new to modeling. And I tell them the modeling is a lot about making a scenario analysis and being able to do sensitivity analysis like this. And when we are finished with this, what we're going to do is we're going to say, okay, if without the round trip efficiency, we needed to put this much power, energy, solar power into the battery, well, we got to put 10% more. And we can just take that, divide that by the 90% and see how much more do we have to put in if we have this problem, again, I'm repeating, of the round trip efficiency. Okay. And then we can take our solar power that we were producing with our solar capacity factor and see how much we need now. And we need more. And when we have round trip efficiency, I was struggling with this a bit, but we need to get at the very end of the day a zero balance in our battery with or without a round trip efficiency. So without round trip efficiency, we made a 1-day analysis, which is elephant in the room, can be criticized, all the rest of it, but we can get it. And so now if we have this round trip efficiency, we need more solar power. Here, let's put some round trip efficiency. Now, it's not exactly the 10% because of the timing, and we use some of the solar power, not depending on whether we've got coincident load or whether we've got off-peak load. We need a different amount because it's the solar power only that increases. It's only the solar power that we use for storage. And once we have this increase in the amount we have, we put the increased solar power. So instead of needing 164 megawatts, we need 181 megawatts to charge the battery because we're going to have losses. All right, that's our problem. And then we'll incorporate that. So let's look at kind of the final result. We have all thermal right now with a 7 fuel cost is winning. If it's off peak, if it's shaped, if our load is shaped and is not just flat, then the solar plus the battery is beating us. Is lower. That's wonderful news. And if we have a longer battery life, it can be really good. But if we have a very flat load, then the thermal is winning. I'm sorry about winning and losing. This sounds American. And then if we have the off peak, then our costs go up. Okay? That's what we can do. Now, there's one more thing to consider, that at least maybe I've missed something. I don't know why I did that one. And that's this depth of discharge. And the different batteries, apparently, again, this is all not very well defined, have a different amount that they can go. And this says a lithium-ion battery has an 80% depth of discharge, and if we put it down, I think your phones are exactly like this. In the old days, if you didn't have a limit, I don't know if there's software in the phones that limit once you get to a certain battery life, they almost shut down because they can really be very, very bad for the battery if you use this. And all that means at the end of the day is essentially we have to get reserve capacity. If we want to think about that in the traditional sense, we have to get reserve capacity to meet our depth of discharge. And here's some other things. And then I can go to learning rate. And then if you look at these slides, I go to how to evaluate ancillary services and how to look at a bulk power cost. And I'm just about finished, I'm so happy about this. So if we put both depth of discharge and the round trip efficiency in here, then this is kind of sad. And maybe let's not be that negative about the depth of discharge. And the good news is we can put all of this in. Let's just put 90% for both. Maybe I'll even give us 92% for the other one. Okay, and then we can look at what if we if we have those two factors considered, the depth of discharge doesn't really affect much of the operation. You just have to buy a bigger battery to get the same output. And that depends if the capacity is stated at the capacity that you can produce if you go all the way down, or maybe the capacity is already stated and the cost is already stated after the depth of discharge. Of course, you have to be very careful about that. And then if we go back to our base case, I'm looking at the solar per plus battery here and getting the result. Now, the final thing to talk about is just that we start adding columns. This is, for me, a really, really big deal, is that you just add the columns across. My friend Max, we're going through hydrogen, and I'm going to have to make another video on hydrogen before I get back to some corporate finance ideas. But once we have these defined, these total amounts of capital recovery, total amounts of operating cost adjusted for degradation, total amounts of capex, then we can just add all sorts of different things together and add the production and make sure we're not double counting, because we're still producing that same amount. And we can produce it with all thermal. We can produce it with solar and battery. And then I made another scenario where we don't put any extra thermal in, and we have much smaller solar. We have much smaller solar. I got a word out. And then we put some thermal for the off-peak periods. And in this case, our best scenario is actually the solar plus the thermal. If we have everything on peak and we have some coincident load, the best option is the solar plus the battery, although that you don't need that much battery, so there's not so much difference. And then if it's totally flat load, we're somewhere in between, and the solar plus the thermal is beating the solar plus the battery cost. And we get that by adding up all the fixed costs and the variable costs. So this file, I think, is kind of important finally. And it took me way too long to do, and I wasted some time, and I feel like crap all the time, because what am I doing wasting time with all of you? And with me, not you. You're not going to be watching this video. And remember, we can look at different solar patterns. Okay, and so that's the end of the